metabolism before I start blabbing, and then if you guys would find it useful for me to go through things like the urea cycle, the ketogenic and glucogenic amino acids, I can do that. But this is going to be my last video, I think, on the backbone reactions and the backbone pathways, the sort of core bit of metabolism. So what you can see here is that I've put up again a really brief overview of glycolysis, this bit, and then getting down to pyruvate acetyl-CoA, and then going through the Krebs cycle. So that's to orient you. And I've written this bit large because this is the step that we're going to be focusing on. You can see we're starting at glucose, so this is the top of the Krebs cycle, the top of glycolysis. This is the very first step. And we're going from glucose to glucose 6-phosphate. All that means is that you're sticking a phosphate onto the glucose molecule in order to send it down the rest of glycolysis. By my arrow notation, you can see that this is one of the irreversible, slow, or controlled steps, okay? And it's catalyzed by this enzyme known as hexokinase, okay? Something that we've sort of been hammering home is that the liver is altruistic and will sacrifice itself for the rest of the body. We've talked about how it does that using glucose transporters and the fact that the liver is only sensitive to glucose in the blood at higher concentrations, whereas the brain and the muscle are sensitive to glucose in the blood at lower concentrations so that they can continue to uptake glucose in times of starvation, whereas the liver will sort of stave off and allow the tissues to do that. Another way that the liver is able to provide the body with energy in times of starvation is by having a different isoform of this particular enzyme, right? So we talked about how the liver can have a different receptor isoform. Why can't it have a different enzyme isoform? And indeed it does. So the liver isoform of hexokinase is known as glucokinase. Okay, so whereas this hexokinase, I think it's hexokinase 1, is going to be found in all bodily tissues. The liver doesn't have hexokinase 1, it has hexokinase 4, which is also termed glucokinase in order to distinguish it. What's important about glucokinase is that it has a Km, we're going to go back to these rate constants, okay? It has a Km of around 5 millimolar. Okay, whereas your average hexokinase has a Km of 0.1 millimolar. Okay, so what this means, if you recall, we go back to the talk about kinetics. Km is your binding coefficient, your binding efficacy. How well does the enzyme attach to its substrate? Well, hexokinase apparently attaches pretty well. Glucokinase, moderately so. In the same way that the transporter, the glucose transporter on the surface of liver cells is only kind of sensitive to glucose concentration, glucokinase is only kind of sensitive to glucose concentration. It's the exact same principle. So the muscle and the brain are always going to be undergoing glycolysis, citric acid cycle, even when the glucose concentration is low, okay? So even in times of starvation, when you have a glucose concentration that is around 0.1 millimolar, which is absolutely tiny, this entire process will still be happening in order for the tissues to get energy out of it, okay? The glucokinase in the liver, however, if the concentration of glucose in the bloodstream drops below 5 millimolar, let's say that we're in times of starvation and we hit 3 millimolar or 2 millimolar concentration of glucose in the blood. At that concentration, this glucokinase simply isn't going to be able to bind glucose anymore, and that will slow down, okay, this entire pathway. And what that means, why that's important for regulation, is that the liver will no longer be using glucose, and it will leave that for the rest of the body. What will happen in times of starvation is that you also have hormonal control, and so due to covalent modification of particular enzymes in this pathway, the liver will actually go backwards and it will generate glucose via gluconeogenesis. So that's when you have glycogen feeding in here, right, and fatty acid feeding in here. And what that's trying to do essentially is, we were talking about thinking of all of these pathways a bit like a pipeline. So what you're doing with this glucokinase at low glucose concentration is that you're essentially putting a block here, right, and you're decreasing the amount of flow through this cycle. But because of external regulation, you're not actually going to, the liver is not going to consume fatty acid for itself. It's actually going to reverse this process in order to export glucose into the bloodstream. Because aside from having this blockage, the other effect, or the other thing that you have to think about is that, well, maybe the body wants to try to keep, this cycle constant at a rate that's high enough for it to survive, but one of the other set points is the level of glucose in the blood. So when this drops, the liver will start sending its pathways backwards in order to try to remedy this in a sort of negative feedback loop, where if the glucose concentration gets too high, it's going to start taking up glucose from the bloodstream in order to bring it back down. But if it gets too low, then it will start exporting glucose in order for the blood and the brain to continue to take it up. So in really dire times of starvation, the liver is really, really trying to keep the concentration of glucose from dropping below this. Because if your glucose concentration drops so low that it's, say, 0.001 millimolar, that means that glycolysis can't happen in muscle cells or in the brain anymore, and that means that you're dead. So I hope this clears up a little bit of how the tissue specificity works, and how different tissues can have different functions when it relates to metabolism. I apologize if the kinetics confused you. If it did, I can either try to clarify, or really you don't need to know the specifics of it. I was really just using it as a tool for explanation. Thanks.